Okay, so last time we're looking at this topological sort algorithm on a DAG. So let us go through one more example and then we'll move on. Okay, so again, what topological sort means? You could get a topological sort of the vertices, that is, a listing of the vertices in a certain order, only if the directed graph is a directed acyclic graph. Means the directed graph should not have any cycle. And so, how we check if a given directed graph is a directed acyclic graph? You run depth first search, and if you do not encounter any baggage during the process of running depth first search, then the directed graph is a DAG, which is what is called a directed acyclic graph. So once you run depth first search on a directed graph, which is also a DAG, you can then list the vertices in the reverse order in which they were popped out. Then that order is what is called the topological sort of the vertices. So each vertex appears in the topological sort exactly once, and the listing and the order satisfies the property that if there's an edge u to v in the graph from u to v, it's a directed edge, then vertex u appears somewhere before v in the topological sort. So for example, in this graph, you say there's a edge from 4 to 3, so 4 appears somewhere before 3. It could be right after that vertex, like for example 4 to 6, 4 appears just before vertex 6, or it could be sometime somewhere later also, like 4 to 2 there is an edge, so 4 appears somewhere before 2. Okay, so let us go run depth first search on this directed graph quickly. You all should know how to do depth first search by now, also on a directed graph, but we'll go through this example. So you could start with any vertex, actually it doesn't matter. So, but as a convention, we'll start with the lower ID vertex. So we'll start with vertex 1. So again, we use a stack for running depth first search. So we push vertex 1 to the stack and visit one of its outgoing neighbors. So again, we break the tie by going to the neighbor with the lower ID. So we go to vertex 2. So that means we push vertex 2 to the stack, and that's the second vertex we push to the stack, and the edge that you used to visit to vertex 2, because you're visiting that vertex for the first time, so it should be called a tree edge. Now vertex 2 is like a dead end, you cannot go anywhere else from there, so it's time to pop out vertex 2. So vertex 2 is the first vertex to be popped out of the stack. So we are back to vertex 1. So you can go to one of its other outgoing neighbors, which could be either vertex 3 or 4. So we again go break the tie based on lower ID neighbors, so go to vertex 3. And again, vertex 3 is visited for the first time, so this edge should be called a tree edge, and you push vertex 3 to the stack. That's the third vertex to be pushed to the stack. So now from vertex 3 we cannot go anywhere else, so we have to pop out vertex 3. So that's the second vertex to be popped out of the stack. So we are back to vertex 1 at the top of the stack, and now we can go to the other outgoing neighbor, vertex 4, and call that edge as a tree edge, because vertex 4 is again visited for the first time. So push vertex 4 to the stack, it's the fourth vertex we pushed. Now from vertex 4 you have outgoing edges to 2, 3 and 6. Now 2 and 3 are already pushed as well as popped out of the stack. So we should call that edge as a forward edge. So you should be careful. So you should not call them as a back edge, because they are not only pushed, they are also popped out of the stack. So if you visit a vertex that has been already pushed and popped out of the stack in the same instance of depth first search, then that edge should be called a forward edge. So that's what we should do for 2 and 3. Now vertex 6 is not visited yet, so you can visit vertex 6 from vertex 4. So we push vertex 6 to the stack, so that is the fifth vertex to be pushed to the stack. Now vertex 6 is again like a dead end, we cannot go anywhere else, so you have to pop out vertex 6 from the stack. So that's the third vertex we popped out of the stack. So far we popped out vertex 2 and 3, so vertex 6 is the third vertex we popped out of the stack. So now we are back to vertex 4 at the top of the stack, and we cannot go anywhere else from vertex 4, so we pop out vertex 4, that is the fourth vertex we popped out. So now again we are back to vertex 1, which we cannot go anywhere else from vertex 1, so we have to pop out vertex 1 also, that is the fifth vertex we popped out. So in this instance of depth first search, we are started from vertex 1 and we are able to visit vertex 2, 3, 4 and 6. So we are still left with 5 and 7, which we could not visit when we ran depth first search from vertex 1. So that means we have to start a new instance of depth first search from one of these two vertices. So let us again break the tie and start from vertex 5. So if you have to decide where to start the second instance of depth first search, again you could break the tie based on the lower ID. You could actually do it from anywhere else. You can start from any arbitrary vertex that you want to begin with, but in this case we'll begin with the lower ID vertex, which is 5. So we push vertex 5 to the stack, and that's the sixth vertex we push to the stack. Now you have two outgoing edges from vertex 5, which is to 3 and 6, but both of these vertices have been already pushed and popped out, visited in an earlier instance of depth first search, not in the current instance. The current instance we just started with vertex 5 by pushing it to the stack, no other vertexes in the stack. So we should call those edges as cross edges. So the edges that you have from a vertex to another vertex that was already visited in an earlier instance of depth first search should be called as a cross edge. So that's what you do for both these edges to 3 and 6. So you don't have any other outgoing edge to any unvisited vertex from vertex 5, so you pop out vertex 5 from the stack. So it's pushed and as well as popped out. So that's one instance of depth first search because no other vertex is now in the stack. So it means 7 is not yet visited. So we are going to run now a third instance of depth first search on this graph starting from 7. So we push 7 to the stack. Now again you have outgoing edges to 1 and 2, which were visited in some earlier instance of depth first search. So we should call these two edges as cross edges. So now pop out 7 from the stack. So in this depth first search, that we ran 3 times on this graph, we did not encounter any back edge in all those 3 instances. So we can call this data graph as a data acyclic graph. And once we decide that the data graph is a data acyclic graph, we can right away go ahead and write the topological sort of the vertices. So the topological sort is by definition is the reverse order in which the vertices are popped out of the stack. That's how you get the topological sort. So that means you can start from 7, that's the last vertex that was popped out, then 5, then 1, then 4, 6, 3, 2. So that's the reverse order. So you could notice that depending on how you break the tie to visit, say, the outgoing neighbors or where to start depth first search, you could get a different topological sort for the graph. So that is fine. So you could have more than one answer for the topological sort depending on how you break the ties as you proceed depth first search. So one thing that you can always make sure you have the right topological sort is make sure for any edge from U to V, U appears before V. So that make sure it satisfies the property. So for example, edge from 7 to 1. So 7 appears somewhere before 1, not the other way. So 7 to 2, again 7 appears somewhere before 2. 1 to 2, 1 appears somewhere before 2. So make sure for, if you want, for every edge that you have from U to V, you should appear somewhere before V. Now I have a small change in this graph where I think I changed this direction. Instead of 7 to 2, the edge is now from 2 to 7. So let us see what happens if you run depth first search on this graph. So you start from 1, go to 2, so you push 2. So from 2 you could go to 7, so you push 7. So now right away you see there is a back edge because 1 has been just pushed, it is still in the stack, and you visited 2, so 2 is also in the stack, and then you push 7. So 1, 2 and 7. 7 is in the top of the stack. You try to go somewhere else from 7, but you cannot because there's no other outgoing neighbor other than 1. But 1 is a vertex that is already pushed the stack. It's not yet popped, it's still in the stack. And the same instance of depth first search. So we should call that edge from 7 to 1 as a back edge. So the moment you encounter a back edge, you can conclude that this directed graph is not a directed acyclic graph, and you can right away say the a topological sort does not exist for this graph because it's not a DAG. Now, if you are curious, you can continue that first search and go through this example and try to practice this example actually, so that you can get to know how to classify edges as tree edges, forward edges, cross edges, and so on. But this is the only change in the direction and in the edges in the graph. So just when I change to one edge direction like this graph has a cycle, and we cannot anymore write a topological sort for this graph. Okay, so if you have any questions, you can ask over the microphone. Let me just save this video.